Hi again, everyone. Welcome back to the Data Idols Summer School, and thanks very much for joining us again. I'm Adam. I'm a technical recruiter at Data Idols. The Summer School is a new pilot program that we're running in partnership with the Data Science Festival. It will run live for 3 months, so you can learn in real time and pick up new skills from the comfort of your own home. These sessions are really sort of designed at an introductory level, so people that are transitioning into data or starting their career in data, it's absolutely ideal. So you can also all use the Slack channel if you're watching this session to kind of speak to other attendees and engage within the community. The Slack channel is Data Idols SS for any event related questions. I'd also like to thank all of our partners who really make this event or this summer school happen. Also to the team at the Data Science Festival and Data Idols who have put in over 400 hours to create this event. So yeah, all sessions will be pre-recorded, so you can watch them back at a later date. That will start in September. We'll be emailing you a link to watch the sessions back. So again, you can learn anything and watch it at your own pace, and it will be available at that time. So today's session is Bayesian machine learning with Egor from Wise. So over to him, and I hope you enjoy the session.
Hi, I'm Egor Kraev, head of AI at Wise, and I will tell you about Bayesian machine learning. Now, what is Bayesian machine learning in the first place? It comes from an idea that's both simple and sounds quite scary at the first step. Namely, in a classical machine learning, which is pretty much all the machine learning you've seen so far, probably, you have a model, which is some kind of a mapping from parameters to data. And you have a goodness of fit function, which tells you how well does your model fit the data. And then you have a data set, say your training data set, and you try to find the best possible parameter vector that fits that data, hence model. This is called model training. The problem with that is that if you're looking for the single best parameter vector, then you might be overfitting. So you might be, this single best parameter vector might be very, very good at describing your particular data set, but not really great at describing the universe you care about. So all the similar kinds of data that you'll want to do inference on later on. And that is called overfitting. And there is a whole cottage industry of regularization methods that arose to combat this. Everything from L1, L2 regularization, dropout, God knows what. And that works as far as it goes. But even if you have regularized your model properly, which is more of an art form than a science, you still have a single point estimate. So if you're predicting, if it's a classifier, that's fine. It outputs probabilities anyway. But for example, if you're doing a regression, your model still gives you one input, one output per one input. And in itself, not a tragedy. And there is a number of hacks that are available for giving you uncertainty intervals around this. But all this kind of model uncertainty management are bolt-ons, which may or may not sit gracefully with your model. In Bayesian machine learning, the story is quite different. You first look at all the possible feasible parameter values. And you start with a prior distribution, saying my parameters can be in this kind of range, which it can be quite vague. And then you're saying, given that I've observed this data from the model, how does that change the probability of particular parameters? So given this data, this area in parameter space becomes much more likely, and this other area in parameter space becomes much less likely. And that is called the posterior distribution. So here, the role of your model is giving you the conditional likelihood. Given this parameter vector, this is the likelihood of observing this data. And then you use Bayes' theorem to invert this, to saying, well, then given this data, these are the likelihoods after observing this data of my parameter values. And so rather than having one true parameter vector, you always work with the whole universe of possible parameter values. The only thing that changes is the distribution, the likelihood or the relative probabilities of the different parameters. As I said, this sounds scary, but actually with these days, there are packages, as I will show, which will make this actually quite workable. So what this means is that rather than fitting one model, we'd in fact fit a whole universe of models, all of which are reasonable fits to the data. And so the output of the model, therefore, is also then not a point, it's a distribution. It's a probability distribution given this input and this probability distribution of model parameter values. This is the distribution of outputs that we're looking for. And so this here plot is a simplest example where you have a regression line, but actually you're seeing the distribution of reasonable regression lines gets wider and wider as you get away from your data. Now, before you get too scared, you don't have to treat all the model parameters in this way. Very often you can just have a single vector of the usual dimension, 100, of dimension of 100 or thereabouts, or whatever suits you, which you treat in this Bayesian fashion. And all the other parameters of your model you treat in a classical way. So why, I'm sure you're asking yourself, do we want to do this? There are pros and cons. So the obvious upside is that you explicitly and naturally represent modeling uncertainty. So you know exactly which parts of the parameter space are allowed by the data you've observed. And so rather than having just one model, you have the whole range. And therefore you know what range of outputs is compatible with the data you've observed. You don't need to worry about overfitting because you know exactly what uncertainty there is and what range of vectors there are. There is no one true vector. Prior knowledge is often very helpful to stabilize model fitting. For example, if you have as you very often do, just some kind of a quite wide area Gaussian as your prior. If you have unlimited parameter values, you have to have a normalized prior. So you typically choose a Gaussian. Then in log likelihood terms, this amounts to the same thing as an L2 regularization on that parameter. But now this L2 regularization has a principled foundation, so you know what you're describing. And another trick, which we will show, or another capability that we'll show towards the end of this talk, in hierarchical models, it allows you to blur the boundary between fitting one model to all of your data and fitting a model for separately for each data subgroup. You can have something that's kind of in between. Downsides. Well, the biggest downside is learning to think in Bayesian terms. It's a learning curve. But on the other hand, and it's taken me a while to wrap my head around this, as it will quite likely will you. But then once you've learned to think about the world in this way, there is really no going back. Once you learn about thinking of everything as probability distributions, this seems so natural that it's hard to understand how you could think about the world in any other way. It can be more computationally intensive, but then again, these days, it's not as much of a problem as it used to be with on-demand compute everywhere and the GPUs being quite fast. And defining prior distributions can be a bit of an art form. So it's something that needs to be learned. But then again, it's more of a feature than a bug. You can always choose very diffuse priors, just saying my parameters can be more or less anything with some kind of a super wide Gaussian, and then let the data define the posterior for you. But you can also use it to inject domain knowledge. So for example, you know the transaction frequency for a customer will be maybe days, maybe hours, but certainly not centuries and certainly not milliseconds. And so injecting this, as I said, is actually great in stabilizing model training. So much for the background. How do we actually do it? How can you work with a whole distribution of parameters rather than a single best model fit parameter vector? Here are two main approaches. The first approach is variational, which means that you approximate the posterior distribution with a nice parameterized shape. Typically just a diagonal multivariate Gaussian. And then you fit that Gaussian over the function that describes the Gaussian as a function of the input data as part of the model fitting. And that's nice and simple and requires very little heavy lifting. The problem is that that approximation is not necessarily a good one. And also this means that the more parameters you fit, the more you have to worry about the shape of those Gaussians. And the other one, which is elegant theoretically, is all the Monte Carlo approaches. So you don't try to approximate the posterior, you just use some magic for a given definition of magic to sample from the posterior distribution directly. So you sample, for example, 1,000 samples from all the random variables you care about jointly in such a way that the average over the 1,000 samples is pretty close to the expected value over the actual posterior distribution. The advantage of that is that it's more general and potentially more precise because you don't assume Gaussianity or anything like that. The disadvantage is that it's much more computationally intensive. So in practice, what kind of software would you use to it? These days, of course, we're assuming Python everywhere. And in the simpler cases, like the Variational Autoencoder, which I will show you shortly, you can code it up in just about any framework you want. As long as you have some kind of optimization machinery like gradient descent, you can just use TensorFlow or PyTorch or whatever you like, really. For the more complex ones, especially if you want to do any kind of Markov chain Monte Carlo, you're much better off using a probabilistic programming language. And this is the magic that I referred to before. So what you can do there is you can describe your model in a declarative fashion, basically write down the structure of your model in math and then transform those formulas from math to code pretty much one-to-one. And then let the framework do the right inference scheme. And from that descriptive specification of your model, generate all the sampling you need. And there are several packages like this. It's always good to have healthy competition. Like PyStan, PyMC3, and Pyro are good examples. And personally, I tend to gravitate towards Pyro because I'm a fan of PyTorch, and Pyro uses PyTorch under the hood. But that's just my personal biased opinion. So let me give you an example of each of those approaches. The first example is the Variational Autoencoder. And by the way, now you know why where the variational bit in its name comes from. That's perhaps the most famous Bayesian model. If you Google the Variational Autoencoder, you will find hundreds of good tutorials on it. And I think you probably will not be able to find an introductory course to neural networks that doesn't mention the Variational Autoencoder. Its structure is, it's more of a pattern than a model. And it's actually quite simple. So you first start with inputs with some kind of complicated structure that you want to capture. Inputs, some kind of inputs, for example, images. Like one application I've seen is you want to classify galaxy pictures in an unsupervised fashion. So you want to see, what kind of spiral galaxies and bulb galaxies, and maybe oblong and whatnot. So you want to classify them in an unsupervised fashion because you have way too many of them. So you start with the inputs, which are images, and you feed them to an encoder. And the encoder is a neural network, which is somehow parameterized. And here, your fantasy is the limit. Presumably, some kind of convolutional networks will be in there, since if your inputs are images. I'm currently working on one where the inputs are sequences, and then the encoder is an RNN, or has an RNN inside, and so on. It doesn't matter as long as the encoder outputs 2 vectors per input. And the 2 vectors are the mean and the standard deviation, which describe exactly this approximate posterior Gaussian, which I mentioned before. And then you sample from that. You sample from that diagonal Gaussian, and that gives you a vector. And this thing is just called latent space. It's just a name. And then you feed this vector to the decoder, which is a second network, which has some additional parameters which we don't treat in a Bayesian fashion. And the decoder produces a likelihood of the inputs given this latent space vector. And that's it. And then you maximize the likelihood of inputs in addition with a penalty term that comes from imposing a prior on how you want the images to be distributed in latent space. And so you train this thing so that the likelihood of the inputs is as high as possible. And then you can just sample from the latent space randomly without caring about any inputs to produce new images. So how does this connect to what we discussed? The decoder, so the second half, is what we referred to earlier as the model. It takes a parameter vector, which is the combination of latent space vector we sampled and its own parameters, and generates a probability distribution over outputs. And then the encoder is the variational bit. It takes some input and maps and converts from this input to the posterior distribution in latent space. And there are any number of tutorials out there on the variational autoencoder, but my favorite one is the one in Pyro, because that's the first time after reading this one that I understood the Bayesian underpinnings of the VA. But this is a lovely trick. And what happens typically, also these examples are also from, these pictures are from that tutorial, is that in latent space, similar things tend to cluster. Basically, this randomization over this sampling and that we don't just pass it through latent space, but actually randomize a bit, enforces a smooth mapping. And then this means that the same digit, so images, for example, here corresponding to the same digit, tend to cluster in latent space. So one very common use of the variational autoencoder is for unsupervised clustering of images. So you train the autoencoder, and then you cluster in the latent space. And then once you sample from those clusters, you can you hope to get more examples. Of course, if your sole objective is to produce more images from a certain universe, you'll be better off looking at it again. But that's just for this particular images example. As I said, for example, you could have a sequence of user actions, for example, feeding in, and have parameters of user behavior being the output of the model. As long as you get a likelihood function at the end, you can train the model. So now for a second half of actually sampling directly from the distribution without trying to, from the posterior, without trying to parameterize it in any way. And that's the whole universe of Monte Carlo approaches. The underlying math I will not try to describe here, but I can only recommend the absolutely wonderful book by David McKay about information theory and inference. And this book is even available in PDF form for free, but I would also recommend just buying the volume. It's a really nice read. And there is also a series of some 12 or 16 lectures by David, which you can look at as a very short summary of the book. And it's wonderful. It's only after hearing those lectures, for example, did I finally understand why entropy is formulated the way it is and what mutual information is and stuff like that. So it's really delightful. I really recommend it. But the good news is that these probabilistic programming languages, such as Pyro or NumPyro, which we'll see an example of shortly, don't need you to understand how any of this works, really. You can just specify your model in declarative fashion, and then the sampling is done under the hood. Let's look at the very specific example that we have. And the example is a spread model. So naturally, as we deal in currencies and we offer currency conversion services to our customers, sometimes we have too little of some currency and too much of another currency. And then we go to external providers like big banks, for example, and we trade currencies with them. And then the spread describes the amount that we pay for this service. And it's typically expressed as a fraction of the volume we trade. So it can be percent or basis points, so hundredths of a percent. Now, if we want to plan for the future, we want to estimate what kind of spread we're getting on a particular currency pair. And the problem we're facing is that some of the pairs we trade a lot, like obviously Euro USD or Euro GBP, we trade on a daily basis. So there we pretty much know what we're likely to encounter. Some other pairs we might trade occasionally, and some others we might want to trade rarely, but nowhere near frequently enough for us to just be able to take a past average. So then we parameterize it. And so what we start out, so this on the right here is the structure of a Bayesian model, of a hierarchical Bayesian model specifically. So first you have the mean and standard deviation of the source currency component. So the first currency in the pair. How much does the source currency contribute to the spread? The second is how much does the target currency contribute to the spread? And then there is a market-based multiplier. We assume that in certain markets, certain counterparties automatically charge us higher spread than others. It's a hypothesis, and then the model will tell us whether it fits well. And then we combine the multiplier and we combine the source and the target spreads, and we combine them using the square root of sum of squares, because the spreads are quite intimately related to currency volatilities, and so and which are like standard deviations in a way. So it's not a bad heuristic when you're looking at spreads to treat them in the same way you would do standard deviations. And here I want a simple model so I can be bothered about correlations, and I just take the square root of the sum of squares. And then there is the pair-specific sigma, which gives the model the necessary slack to fit even currencies where we have lots of data. So let's briefly switch then to how this would work in NumPyro. So I import all the data, and this is what our raw data looks like. We have a timestamp, the spread as a fraction of the notional we traded, source currency, target currency, market, and please ignore the other columns. And here are some summaries. So for some of them, they're reasonably tight, but you can see that here, for example, for the Aussie Euro spread, the standard deviation is actually larger than the mean. So this is very noisy data. We set up some label encodings that transform currencies and currency pairs into indices. And here is for the fun part. So we have this model structure, and here is the model. So first of all, we're setting up the priors. The mean and standard deviation for the source spread. And you can see the standard deviation is super wide, especially considering that because we want the spreads, both the source and target spread, to be positive, because it's very unlikely that we will get paid for the service rather than us paying the provider. Then it's on log scale, and we have this super wide standard deviation for the prior. Same for the target, and quite a wide multiplier, quite a wide prior for the multiplier, but not quite as wide. And we see the sigma that we use for the pair-specific adjustment is much tighter. And that is where this thing is a bit of an art form, where you want to see, if you have this model with lots of moving parts, you can control which moving parts should be more responsive and adjust more, and which moving parts should be rigid. Then you're saying, well, okay, so this is so these were the global priors for there's just one number or one random variable. Now for the spread, you define an array of random variables. So which is a plate, a variable in Pyro slang. And you're giving as many of them as you have unique source currencies. And all of them are log normal. So their mean, so each of the spreads is a log normal sample from the prior. Same for the target. And same for the market multiplier. There is just one trick for the market multiplier, which is that the model in this way is badly conditioned, because if we multiplied the market multiplier by a factor of 10, for example, and at the same time divided both spreads by a factor of 10, we'll get the same result. So there is no single optimum if you do it this way. And one somewhat hacky way of pinning down this optimum is to forcing the market multiplier to equal 1 for a particular provider. This is the market special index. And then hoping that the rest will be anchored by that. Then here is the square root of the sum of squares formula. And here we apply the market multiplier. And finally, we do the sampling for, we add the pair specific noise. And then finally, we say that each observation of a spread is distributed with this pair spread mean and some kind of ambient noise, because each observation will be different, of course. And this, by the way, is where we plug in the data. So this is the only and final point. So none of these intermediate values, or the source or the target ones or their priors, are observed directly. The only thing we observe is the final spreads, so final link in the chain. So which is why this is also great for modeling latent variables. But you see that this is pretty much a straightforward one-to-one translation from the mathematical formula to code. And now comes the magic. You just say, this is a nuts kernel. It's a particular kind of sampler and no U-turn sampler from the model. And then you say you want to run Monte Carlo on it. And first you want to warm up for 3,000 iterations. And then you want 2,000 samples from the posterior. And those are each of those samples is a sample of every single random variable in your model. And then you run it. And that's all there is to it. And then you can see here, it takes a while to run. This is the biggest downside of Monte Carlo methods. It takes almost an hour to run. And then you can plot the posteriors for the global priors. They're on the log scale, that's why they're negative, and for all the individual spreads. Now, what you now have is a model object, which it might look like it's not really very much good to you. But then in this cell, we get the samples out of the model. So we're saying we want the values for these model variables. We specified those names when we're defining the model here. So these are the names that these things have. And now we're saying we want those 2000 samples that we generated just for these variables. Sometimes it's faster if you don't want everything, but just the variables you care about. And then you get a lovely matrix, 2000 samples, and these are the 67,000 different variables. Remember, there's quite a lot of pairs, quite a lot of currency combinations that were sampled from. And that's all there is to it. That's the beauty of probabilistic programming. You do have to twist your brain to make it work, but the actual code is quite concise and beautiful. Now let me go back to the show. So now you've seen both sides of it, the variational kind and the Monte Carlo kind. And hopefully this is enough of an introduction to give you a flavor of what Bayesian models are good for. Or as you've seen, it's not even that there are Bayesian models. You could take any model and fit it in a Bayesian fashion. It's just a way of thinking about whether you want to look at the best parameter vector or if you want to look at the space of possible parameter vectors. Now, summing up, when in your actual working life should you use these things? The first obvious one is anywhere where understanding model uncertainty is important. One application that we are working on right now, for example, is understanding customer behavior, and then a customer that you have observed for years, that has been with you for years, you probably have a pretty good idea of what they're going to do next. A customer that has just joined you, much less so. But using Bayesian models allows you to quantify that uncertainty and to quantify how much more confidence you get in their behavior, in predicting their behavior as you observe them for longer. Another use case is, like I've just shown before, anywhere you want to capture fuzzy effects, where in hierarchical models, you can say, well, I have my priors for the data set as a whole, my expectations of the parameters, but then for each particular subgroup, I have a specific realization. And then if I have a lot of data for that particular subgroup, then I can pin down the specialization very precisely. But if I have almost no data, I still know this data is sampled from the prior. And therefore, I have some handle from the data set as a whole. And it's not just an either or, for there is this whole spectrum in between that's handled gracefully and simply. And the final use case, as you've always also seen, is when your underlying process is highly stochastic. And you cannot observe all the variables that you care about. For example, you don't actually know whether your customer has churned or whether they'll come back. And then the churn for most online services cannot be observed because people don't cancel their subscription. They just don't come back and don't use the site anymore. And so for working with those kinds of latent variables, Bayesian approaches are nice. And that last example is not actually taken at random. So as I mentioned, we are currently working on a Bayesian customer behavior model. And hopefully, if it does what we hope it will, we hope to open source it later this year. All right. And I hope this has been useful. And if you want to start playing with Bayesian models, please don't hesitate to get in touch with me at firstname.lastname@wise.com. Thanks a lot.